Here in this video, we would like to draw PV diagrams, that is pressure and volume graphs, and represent the graphical way and see how much of the work done in different kinds of processes. Let us start with by talking about a kind of a case where pressure is constant, which is not varying. Pressure is constant. The process in which the pressure is kept constant could be called isobaric process, right? So we would like to talk about a process called isobaric process, the process in which pressure is kept constant. So if you draw a graph between pressure and volume, taking the volume on x-axis and pressure on y-axis, in the case of an ideal gas, say at a constant pressure, you have raised the temperature so that the volume is changed from one value to the other value. Say volume has moved from V1 to a new value V2. So the respective graph will have a square or a rectangular shape as shown, who is having some area inside. Inside the graph there is some kind of a area. Now if we have to calculate what is the work done in this process, if we want to calculate work done in this process, we know the formula for the work done as at constant pressure P dV. Pressure is P, dV is change in the volume V2 minus V1. So how do I get it? Pressure is on y-axis, dV is on x-axis. So when you find area of this rectangle, so in from the graph, if you want to calculate the work done in the graph, work done can be nothing but area of that graph, or else area under that curve. So this is the line that we have. Area under that is whatever I have shaded it in a yellow part. If you find that area as something like, say this is area is of this part is length into breadth. Length is varying from 0 to P and breadth is changing from V2 to V1. If you write whatever the values that are available in the graph, you will get the value of the work done from the graph also. That is when the pressure is kept constant. Suppose if the pressure is not constant, if pressure is not constant, the process is not an isobaric process. The pressure is varying with respect to time, temperature. Volume is also varying. So volume is varying, pressure is also varying. And if you draw a graph, let the graph is like this, because this graph is not parallel to x-axis because pressure is also variable. So here there is some pressure, here there is a different pressure, here there is some volume, here there is some different volume. In this case, if you want to calculate the work done, as pressure is also variable, you have to integrate to get the total work done. And if you want to get it from the graph, if we have to get the work done, we have to find area under that curve. So I will shade with a color and show you what do you mean by area under that curve. See, this is the curve. So under that curve, whatever this area I'm just shading now, we have to find out the area of that part, this entire area. How do you find that area? You can find area of this rectangle using a length and breadth. Of course, rectangle is extended up to here. Above that is approximately a triangle. You can find the area of the triangle. Sum of both that areas gives the total work done in that process. When the pressure is also variable. So when the pressure is variable, it's not a straight line. It's going to be a kind of a curve. We can further say in the process, if volume is increasing, we can say work done is positive. Similarly, here you can see volume is increasing from V1 to V2. If it is happening in reverse and if volume is not increasing but decreasing, respective work done shall be treated as a negative in terms of a sign convention. That's next case. Let's talk about another scenario called process called cyclic process. The process that goes back to the initial place itself, wherever it has started, is called like a cyclic process. If you draw a graph between volume and pressure in a cyclic process, volume on x-axis, same pressure on y-axis. Say it starts from somewhere, it goes and comes back. It has moved from A, B, C, moved back to C, D, A. That kind of a process where it comes back to its initial state of pressure and volume after certain time is called something like a cyclic process. So one thing that you need to understand in cyclic process is in this cyclic process it came back to its original state. That means its internal energy is equal to 0. Being internal energy is equal to 0 mean to say final internal energy equal to initial internal energy. According to first law of thermodynamics, dq equal to du plus dw, but the du equal to 0. So in the case of cyclic process, what all the heat supplied is used to do the work. It don't have anything like to do with internal energy. Now, what is the work done in this process? If we have to find out work done is, there is, you can see, if you see work done during A, B, C is volume is increasing from V1 to V2. Whereas work done during reverse CDA is volume is decreasing. So during AB work done is positive, ABC. During CDA work done is negative. Anyway, what the total work done means, what I need to do is, I have to find out the total area. Yeah, I'll write it here first. Total area under upper curve ABC minus total area under the lower curve CDA. Let me tell you what's the meaning of total area under ABC with a kind of a yellow color. So from this, you draw a line. So it will come to the bottom this way. My lines are exceeding a little because of the sketch pen, but that's the total yellow. Now, if you want to know the total area under CDA, this is whatever CDA is. So under CDA, you shall draw a line. So whatever is greenish now. So if you remove area under CDA from the area under ABC, what is remaining is area of the PV graph within that closed path. Within that closed path, if I have to show you, I have to show you this way. If I remove that yellow to green, you will get this pinkish one. So that is the work done, right? That's the work done in the case. That's the work done area of that closed path. So in a cyclic path, area under that closed path has to be identified, right? That is what do you mean by a cyclic path PV graph, right? Now, I also want to tell you a few things like I already discussed about isobaric process. Let me tell you about another process called something like if somebody say the process is the isochoric process. So I can title this as work done of different processes. We are also talking about different processes here, right? Yeah. Isochoric process means the process in which volume is kept constant. When volume is kept constant, change in the volume equal to 0. Work done, we know PdV. As change in the volume is 0, in this case, work done is 0. As work done is 0 in the isochoric process, according to first law of thermodynamics, dq equal to du plus dw. But dw equal to 0. So dq equal to du plus 0. So dq equal to du means in isochoric process, what all the heat energy that he has supplied is used to increase the internal energy of the system and no external work is done. Right? As we have started with this, I just want to conclude by saying one more small thing by talking about the slope of the PV graph. So when you draw a graph between volume and pressure, we know we have learned about two kinds of processes called isothermal process. Isothermal process where temperature is kept constant, wherefore PV equal to constant. And we have another process called something like adiabatic process. Adiabatic process. In this process, temperature is not constant, therefore Boyle's law is not valid. It is not PV constant. PV power gamma is constant. So it's very clear that slope of adiabatic process is more curved than the isothermal process. By how much? Gamma, because power gamma is there. Gamma than isothermal process. So we are talking about just the slope also, so that we can conclude about PV graphs that we are talking, right? That's how we shall understand the PV graphs. Thank you for watching. You can revisit the entire video and see it and write a notes of yourself so that you will have it as a reference for you. Thank you for watching.